Hello, everybody, and welcome to our webinar. We appreciate you joining us today to discuss green hydrogen, ultra-pure water, and electrodeionization solutions. Today, we'll be hearing from the three subject matter experts from Evoqua Water Technologies, and we'll focus on deionization needs in hydrogen production. So let me introduce our speakers. First, we have Michael Cavallari, a leading sales manager specializing in IonPure. Next, Pat Buzzell, the Director of Product Management with over 24 years of experience in water purification and high purity water systems. Last but not least, Clark Briggs, a sales manager with over 18 years of experience in ultra pure water industry. So let me turn it over to Michael to get us started.
All right, thank you, Allison, and thank you all for tuning in. Today we have a very informative presentation for you on the ultra-pure water needs for hydrogen production. As many of you know, hydrogen production is a rapidly growing industry. So before we get started, let me review today's agenda and the topics we're going to cover. So first off, I'm going to provide an introduction to Evoqua and IonPure EDI. Then Clark Briggs will review the ultra-pure water needs in the production of green hydrogen. He'll also provide a comparison of the EDI process to the mixed bed DI resin process. And then Pat Buzzell, he'll take it up and provide a technical overview of how EDI works. And then I'll give you an overview of our product offering. And then next, Pat will present the operating cost comparison of EDI versus mixed bed ion exchange. And then we'll wrap it up with some frequently asked questions. All right, so first off here, I'm going to give you a little bit about Evoqua and IonPure. So Evoqua is a publicly traded company on the New York Stock Exchange. You'll find us under the call letters Aqua. IonPure, EDI, is a product of Evoqua Water Technologies. So this is a product that we developed and wholly own. We've been working with EDI for over 30 years. In fact, some of our original inventors are listed on the patents. They're still with us today. We've got a worldwide sales and technical team supporting IonPure. IonPure is manufactured in two locations, in Tewkesbury, Mass, and Singapore. We also have research and development at both of those locations, bringing new products to market all the time. Our team is mainly focused on sales and distribution through OEM manufacturers, or OEMs, and systems integrators. And what that means to you is that we build the modules and the power supplies, and then we rely on our value-added OEMs to build the systems and the skids while integrating EDI with other equipment into a total solution. So one of the things we'd like to point out, we have one of the most complete ranges of EDI products on the market, and I'll go through those products in a little while. We also encourage you to visit ionpure.com, where you'll find many resources, including complete product support, including technical documentation and specifications, product data sheets. You'll find engineering bulletins there, software downloads. There'll be sample P&ID diagrams and much more. We also have an online projection tool called IP Pro that allows you to input the RO feed water quality and then output the EDI water quality. This can be very helpful when designing new systems. All right, so I'm going to turn it over to Clark, and he's going to review the ultra-pure water needs in production of green hydrogen.
Thanks, Mike. So now that you know a little bit more about IonPure and kind of the support we offer to the market, we thought we should first cover what role ultra-pure water plays in the hydrogen production. Next slide. So what we're going to do is review a couple of the most common electrolyzer methods right now that are coming to market, and to review where the ultra-pure water is needed, what quality level is needed, and just like a high-level overview of how these designs work and the water part that integrates into them. So first off, we're going to look at the alkaline electrolysis method. This actually is one of the oldest methods to make hydrogen. It's kind of coming into a new heyday where there's some decarbonization efforts and technological advancements that are really pushing this back into a viable production method for hydrogen in a lot of applications. So looking at it, kind of orienting where we are, it all centers around the electrolyzer. So as with any electrolyzer that's in hydrogen production, as the name implies, you're going to be applying an electrical voltage to this system to generate the hydrogen. The main important part that we're interested in, kind of where the ultra-pure water goes into this system, is this bottom loop right here. So orienting yourself with this blue box. So this is the DI makeup that's required into that system, and then it feeds into the lye tank. So as alkaline implies, this is a high pH process. So the DI water goes into the tank, it mixes with a potassium hydroxide solution, and that circulates within the electrolyzer as you're producing hydrogen. The key thing to understand is that the alkaline and the potassium hydroxide is not consumed. So it's basically returned to the system. So the only real input becomes that DI makeup water. So what kind of water is required? So looking at alkaline, and because of that nature of that, that potassium hydroxide kind of buffer, the water quality requirements are not super stringent. It's greater than 1 megohm resistivity or 1 microsiemens. So it's clean. It's ultra pure, but it's not to that really super high extent, as we'll discuss later. But it's better than you're going to be able to hit with RO, even 2-pass. You're really going to struggle to get down to 1 microsiemens or lower. So just it's kind of basically like type 1 or type 2 water, I should say, for those that are familiar with the pharmaceutical industry. So it's clean water. It's just not super stringent, but in essence, it is going to require some demineralization technology. One of the key kind of footnotes that we have highlighted here in yellow up there is the flow rate that's required. So within the system and within any makeup water to any of these electrolyzers, there's kind of a rule of thumb. It's about 1 gallon per minute per megawatt of stack size. This is a direct correlation to what's lost in hydrogen and oxygen production. So if you have a 5 megawatt stack, you're going to need about 5 gallons per minute makeup water into this electrolyzer. And again, the requirements are not super stringent in alkaline, but it still needs demineralization technology. Next slide. So the second process we'll look at is PEM electrolysis. So this is proton exchange or polymer electrolyte. It's kind of synonymous for the same process. And I apologize, we do flip-flop. So the makeup now is at the top, but it follows that same kind of flow rate that's required. We're still at that 1 gallon per minute per megawatt of stack size because that's what's lost, obviously, when we're generating. But the main key, difference between alkaline is that PEM requires a very clean, high purity, ultra pure water. And the reason being is that this is a water only process. There's no caustic solution. The only electrolyte that's circulating through is ultra pure water. So that water bumps up to where it needs to be greater than 15 to 16 megohm resistivity. This is like 0.067 microsiemens. It's very clean, very, very much into the ultra pure world. It's pretty close to type 1 water for those that are familiar with the pharma standards. And it definitely is that ultra pure water that's needed for that makeup. But again, it's the same flow rate, just much cleaner water. The second part that you can kind of see as you go down is that there's another demineralization portion that's involved with the PEM process. The reason being is since you don't have that buffering solution, you really need to keep that water clean to keep that stack efficiency way up there where it is. And that's why PEM has caught on, is because of that stack efficiency. And the DI polish is required to basically remove anything that's being generated in the process that you don't want sticking around in that loop. So the DI polish gets there, it keeps it at that 15 to 16 megohm resistivity. But the key thing to understand about what's required about that DI polishing loop is that it's a high velocity, high temperature process. So the flow rates that we've seen can track anywhere from 15 to 50 times that megawatt size. So if we go back to that 5 megawatt stack that we had, we could be at 75, 200, 250 gallons per minute on that loop just to keep that water clean. And as I mentioned, it also runs at a high temperature for efficiency in the system. So typically we've seen around 60 C is where those have been running on that polishing loop. So the key takeaways, so alkaline, same amount of feed water, not too stringent requirements. PEM has 2 steps of deionization involved with it. Same makeup amount, but it does have this high flow polishing loop. Next slide. So now that we talked about, okay, so I need ultra pure water for both of those processes, albeit a little bit less for the alkaline. What are my options? So typically what people are going to think of, kind of the legacy products would be ion exchange tanks. So you would have mixed bed resin that's in a tank that you're renting from a supplier. They bring it to your site, they hook it all up, they have regenerated at their facility, you run it, and when it exhausts, they come pick it up, bring a brand new tank to you, and take it back to their facility to regenerate it. So that process inherently, there's not a whole lot of capital because the supplier owns all of the equipment. They own the resin, the tanks, the trucks, the regeneration system. So they own all of that kind of infrastructure to give you the tank. So what ends up happening is they're renting it out to you. Obviously, they're going to be making a profit. So they're going to rent it out to you at an added cost of what it actually costs to do the work and get it done. So it becomes an all OPEX solution, in totality. So the other key thing about, that besides it being costly is that they are going to limit what temperature you can operate on. Remember, I mentioned that there's a high temperature loop in that PEM process. So they're really going to cap it around 45, 48 degrees C, because what ends up happening is you're denaturing the ionic resin in the bed if you run it anything higher. So basically the name of the game for the service supplier is they want to keep that resin life. They got to regenerate it and use it for several years. So they keep that temperature limitation to make sure that their resin stays intact. So that's a key kind of limitation that would be on rental resin. The second option right here in the middle is single-use resin. So what this is, as it sounds, is you own the tank, you're adding the resin as it comes in bags, you'd be adding it to your tank, filling it up. You would run your system till exhaustion. When it's depleted or exhausted, you would take that resin out, dispose of it, either landfill it or some other method of disposal, and then you would add brand new resin to it to start again and run your tank again. So it's very costly. You're basically purchasing new resin every single exchange you're doing. Not to mention the sustainability for us is challenging, given that we're talking about green hydrogen, and we'd be throwing away a good portion of this process. So it seems very unsustainable, especially at high flow rates if we're getting into some bigger size systems. The one thing that it does do is it allows you to run at 60 C. So it does overcome that limitation, and because of the way it runs, that single use, you basically are killing the resin, but since you're only using it one time, you don't need to be able to regenerate it. So you're destroying the resin as you're using it at high temperatures, thus why you have to throw it away when you're done. So the last option on the right is kind of why we're here on the call, which is electrodeionization. So what this is an on-site purification system that's going to hit all the requirements that are needed for either the alkaline or the PEM process. Since it is on-site, it is a capital purchase, but as you'll see, and Pat will run through, the OPEX is extremely low. It's just electricity that runs this process. There's no chemicals, so it's electrically driven. And the other benefit is that it can run at 60 C. We're not limited to the, regenerable ion resin. And so it does operate at 60 C, and it is a continuous process, which Pat will get into. But those are your three options, really kind of how do you get there within these, these electrolyzers. Next slide. But first, I do want to kind of take a step back. We talked about my options, but kind of how do they work? I know there's varying degrees of water expertise on the call, but I think it's important that we look at how ion exchange works. With the rental resin or with the single use, the functionality is going to be the same. So the principles are, when you have mixed bed resin, you have both cation and anion resin. It's swirled together, so you have a homogeneous mixture of both resins so that it equally will treat your water. And they're charged with hydrogen and hydroxide respectively. So when it comes either from the rental supplier or from the bags, this is the form that it would come in. So it's in your tank, and then when you add the water that you're trying to purify, you're going to have ions that are in there that you want to remove. Here in the picture, it's sodium chloride. And the reason this works is that the resin actually wants to be attached to the sodium or to the chloride more than it wants to be attached to the hydrogen or hydroxide. So what ends up happening, as the name implies, there's an ion exchange. So that sodium attaches to the resin, the hydrogen comes off, and then in the anion resin, that chloride attaches to the resin, the hydroxide comes off. And so the beads are now fully attached with all the ions you don't want, and then you are left with hydrogen and hydroxide. So thus, you have Ultrapure as the net product. So I know that was a 30-second review of kind of how the ion exchange works, but as Pat describes EDI, it's important to know how this works and then the various differences that we have in EDI and that functionality. So with that, I'll hand it over to Pat, and he's going to review how EDI works.
Great, thanks, Clark. So yeah, in this section, we're going to dig in a little deeper to one of those three typical options for deionization and hydrogen production via electrolyzer. So first off, I just want to bring your attention to this picture on the screen. So this is an installation using the LX platform, which we're going to talk a lot about today because it has some unique capabilities to run at 60 C or hot temperature continuously. So this is a system that has 450 LX modules and operating at about 6,000 gallons a minute. So we can build very large platforms out of this this module, the LX module. Next slide. But to dig in a little bit more about electrodeionization, we're going to take a quick step back. And for many of you, probably this is a little bit like going back to chemistry class here. But essentially, if we had, say, a beaker of water and we had two electrodes inside the water, one of them positively charged, the anode, and one negatively charged, that's the cathode. And then we pour in just sodium chloride, so regular salt. And what would happen is the salt would dissociate into positively charged ions, which are called cations, and negatively charged ions, which are anions. So now you have the fundamental physical process where opposites start to attract. So sodium, which is positively charged, is going to be attracted to the negatively charged cathode. And on the other side, the chloride ion, which is negatively charged, is going to be attracted to the positively charged anode. So those two will actually start to shift and move. Now that process in and of itself doesn't really help us to treat water very well, but it does set up the next process where we add ion exchange membrane and actually take advantage of this phenomenon. Next slide. So here we're really describing a process called electrodialysis. So this is designed really to treat brackish water salinities, higher salt levels, and it works very, very well there. But the basic premise, if we look at the three streams on that picture on the right-hand side, just to orient everybody on here, the thing that we've changed in this process is now we've got these channels, and these channels are separated by ion exchange membrane. And the blue membrane is referring to cation transfer membrane. So that allows cations only to transport through, but not anions. And then the green membrane that's in this visual is the anion transfer membrane. So that's the opposite. That allows the anions to transport through, but does not allow cations to transport through. So in this example, now I'm going to bring your attention to the middle column, and this is what the one that's labeled pure water. And what we call this is the diluting stream, because this stream is an area inside an electrodialysis cell where ions can only leave. And to give you a quick example of that, we'll look at the sodium ion. So the sodium ion in the middle channel is positively charged. It physically is attracted to the negatively charged cathode. And the first membrane that it comes in contact with is the cation transfer membrane. So since it's a cation and it came in contact with a cation transfer membrane, that ion is allowed to transport through the membrane. So effectively, it moves out of that middle channel into what we call the concentrating channel, which would be the waste stream. And the same thing's happening with the chloride ion. That's a negatively charged ion. Again, I'm looking in the middle of the cell. And it's the first membrane that it comes in contact with as it wants to shift towards that positively charged anode is the anion transfer membrane. So because it's an anion, it can transport easily through the anion transfer membrane. And again, now we've got anions moving to the right and sodium ions moving to the left, effectively leaving this area or diluting and purifying that stream. And then on the outside cells, those are concentrating cells. So those are areas where ions can only enter, but they can't leave. And a quick example of that would be if we were to look at the positively charged on the right-hand side. If you look at that positive charged sodium on the channel all the way to the right, the sodium ion is positively charged and is attracted to the negatively charged cathode. But because it first comes in contact with an anion transfer membrane, and again, remember, this is a cation, so it comes in contact with an anion transfer membrane, it can't pass through there. So it's really stuck inside that channel. And this is the basic process for how we're able to purify water. And again, this is more oriented towards brackish water, higher salinity water, but it is a process that allows us to start to purify water. One important difference about this process, this is not pressure driven. So it's not like an RO membrane where the pressure is driving this overall process. The electric field is what's driving this process, and it allows current and ion transport. Next slide. So in order to make this something that can treat ultra pure water, there is one necessary addition to that process that we just reviewed for electrodialysis, and that's the addition of ion exchange resin. It's essentially the same resin that Clark was describing earlier, is the resin that we would use inside our module to help us reduce the resistance of current through ultra pure water. Because if you remember, ultra pure water is actually resistive to electrical current. So if it's got lots of salt in it, like a brackish water, electrodialysis can work. But when you get ultra pure, that becomes a very resistive process in order to start to transport ions. So the addition of ion exchange resin is the media that allows us to do that. Next slide. So now we're going to bring all of it together. So now we've got the basic physical phenomenon where opposites attract. We've added the ion exchange membrane. And now we've also added the ion exchange resin, again, to reduce the resistance and allow us, it kind of acts like a superhighway, allowing us to transport the last remaining ions in an ultra pure water feed to deionize the water. So in this, it's a little bit different than the first one. In this one, the center channel is the concentrate or reject compartment, or also I refer to it as the waste stream, and the two outside channels are the diluting streams. But the basic premise that I described in electrodialysis is at work here as well. The one thing I wanted to add a little bit more context to in this example is the continuous regeneration of this process. So if you think about, if the feed water is coming from the top to the bottom and we're constantly transporting ions out of the water from the diluting stream into the concentrate, at some point in time, there's not a lot of ions left to transport, but we still do have an electric field there. So that electric field is there and current is being driven there. And what happens on a very localized level is that energy is used to split water. And when you split water, you actually create hydrogen and hydroxide, something we were talking a lot about today, right? So in that process, again, on a very localized level, we've actually created regenerant chemicals. And those regenerant chemicals allow this resin to stay ultra pure. So as long as we have current flowing through this and we have water splitting, this process continues and we constantly regenerate the resin bed. Next slide. So the big benefit of that continuous regeneration is that this process is, as the word describes, continuous. So there are no dips, there are no changes in performance over the life of the module. The water quality stays the same. And because they're designed to run constant operation and constant purity, they also automatically adjust to different temperatures and can constantly get the right amount of amperage to drive the performance that's needed. Contrast that a little bit with a typical deionization process using ion exchange resins. So the left-hand side is a typical ion exchange process where we're going through some type of regeneration. And no matter what, we're really looking for signs where that bed is starting to exhaust. So Clark described ion exchange a little bit earlier, and we saw that it was exchanging essentially sodium and chloride for hydrogen and hydroxide. When you start to fill up all those available sites, you start to exhaust the resin. And when you're doing that, the water quality that comes off of that ion exchange resin starts to degrade. So it's very common for operators of ion exchange systems to start looking for signs that the bed's starting to exhaust. One of those ways is they look at silica removal, which is a weakly ionized contaminant, and it tends to come off before the rest of the resin starts to exhaust. So no matter what, though, you're looking for signs of degradation before you know it's time to either exchange the resin if you're using single use, or if you're getting service resin delivered, to make sure that you put in the new service resin in bottles or systems that are being shipped to you. So that is one critical difference between the two types of technologies. One is very batch oriented and the other is continuous. Next slide. So now I'm going to turn it over to Mike Cavallari, and he's going to give you an introduction to the IonPure products. Mike?
All right, thank you, Pat. All right, so what you're looking at here is an example of a nice compact EDI skid. And before I get into the individual products in the next slides, just want to point out a couple of things on this skid. If you look at the upper right-hand corner there, you'll see the electrical panel, and inside there we house 3 power supplies. So each power supply running a module here. You'll notice the white housing, that's our VNX module. And these will run at 55 gallons a minute at nominal. So the skid is roughly 150 gallons a minute in a nice small space on the floor there. You'll see the Schedule 80 PVC. Everything's nice and clean. There's a manifold here and the piping and so forth puts together a really nice example of an EDI system. Next slide. All right, so this slide here I like because it gives you an idea of the flow ranges. I've mentioned earlier we have a very complete product line. Starts with the Lab XT, and that product will flow at roughly a fraction of a gallon a minute. And as the name implies, it's used primarily in lab applications. The next product is the MX series, and this will run a few gallons a minute. And that leads us into the LX series, and that runs roughly from 4 gallons a minute up to 22.5 gallons a minute at nominal. And we've got the 60C listed here. That's because this is the most ideal product for the hydrogen production market. We have an LXHI version of the LX modules, and that is for hot water. The CEDI is a module that is a variant of the VNX, and it's used for high scale applications or high hardness in the water. And then the VNX module itself, it runs roughly from 12 gallons up to 100 gallons a minute, and nominally at 55 or 66 gallons a minute, depending on the model. Next slide. All right, just to show you visually what these products look like, on the upper right-hand corner, you'll notice the Lab XT module. These are fairly small, couple of pounds. You could hold them in your hand, and again, fractions of a gallon a minute. The MX series on the left there, upper left, is the lower flow model. This will run a few gallons a minute. These modules, depending on the size of it, it's roughly the size of a football. You can hold it, it's maybe 5 to 10 pounds. And then the LX series on the right, this is really the workhorse here, the one we've been referring to. These will run anywhere up to a couple of 100 pounds. And as I mentioned, 22.5 gallons a minute at nominal for the largest. And then you'll see our VNX high flow module on the left, that could run up to 600 pounds. And then on the right-hand side, the DC3 power supply. So this is an overview, very brief overview of our products. Next slide. Just to target the LX series, this is the LXHI series. So it's for continuous hot water up to 60C. And you'll notice the various flow rates here and the different models. So starting at the top, the LX04 has a nominal flow rate of 2 gallons a minute, and then the LX45 up to 22.5 gallons a minute. We have thousands of these modules installed around the world. Very dependable and proven technology, used widely in a lot of different industries. So this is a great product for the hydrogen application. Next slide. All right, I'm going to turn it over to Pat Buzzell, who's going to go through the operating cost comparisons of mixed bed DI versus CEDI.
Great, thanks. I think this is probably the part that everyone's been waiting for. So again, just to reorient everyone, again, Clark described this PEM electrolysis process earlier, and that's what I'm really going to focus in on a little bit more, because outside of the makeup requirements, which again are about 1 gallon a minute per megawatt, this also has a recirculation loop, and that recirculation loop right now runs continuously at 60C would be ideal. So if you have a technology that can operate inside there at 60C, then there's no need to do any auxiliary chilling. But if you had a technology that was in that loop that could only operate at a max of say 45 to 47 degrees Celsius, then there would be some type of a need to chill that water so that when it enters into the ion exchange resin bed, there's no change to performance and operation of that ion exchange material. unless of course it's single use. So we're going to take a look at specifically some of the costs and operating expenses for this process. Next slide. So first off, we talked about the fact that if you are operating a technology that can only run at about 45 C, and the electrolyzer wants to run at 60 C, there will be a need for about a 15 degrees Celsius drop. And our estimates for a 125 gallon a minute system would be that the annual cost of that would be around $31,000. So that's operating a chiller that's about 150 tons. And the equipment costs outside of the additional 31,000 of operational expenses would also require some capital costs to allow this process to happen that we estimated about $90,000. So what I want to kind of guide everyone to is the fact that we've talked about a couple of times, LX modules, specifically the module LXHI that runs continuously hot at 60 C, would not incur those additional costs. So the 31,000 goes away because we can operate continuously at 60. The other thing that goes away is the capital expenditure of the chiller that would need to be in that place if you did need to chill it. Next slide. So there's a lot of information being presented in this next slide. And we've got some nice tools that we've put together that allow us to very easily put together some comparisons of operating mixed bed ion exchange systems and comparing them to electrodeionization. So there's a lot in there and we make some assumptions, but again, if you were to ask us about doing one of these where we're putting or incorporating the actual plant numbers that you would have or have access to as far as costs, we can update them a little bit. But in general, I think it gives you a pretty good picture of the differences between the two technologies. So there's two pieces to the operating costs that I'm going to point out in this example. One is the cost of actually doing the regeneration. And then the second cost I'm going to talk about is the cooling requirements. So in this, we estimate that the cost of operating a regenerable mixed bed system and then renting it from someone else that is, again, doing the regeneration work would be about $14,500 a year. And right now I'm looking at that operating cost box in the lower middle of the screen. So about $14,500 per year for rental costs for a mixed bed ion exchange process. And then the auxiliary cooling requirements to operate that would be another $31,000 a year. And that's again, the number that we had talked about on the previous slide. So all total, we would estimate that this process with the cooling and the cost of the regeneration that would be incurred by the service company that you'd be using would be about $45,600 a year, roughly in that neighborhood. And if you go to the right-hand side, here we're describing just the electrodeionization process. So we talk more about, all right, what are the costs of electricity? What are the costs of modules? And then what are the costs of the actual maintenance that goes into this? And because we're operating on an ultra-pure water loop, the actual costs or maintenance requirements are very, very low. In this example, we're estimating that cleaning with typical cleaning products that's similarly used on RO systems would be cleaned once every 2 years. But what we do know about operating many systems that are in ultra pure loops for semiconductor is in those applications, it's common where we haven't had to clean them in 5 to 7 years. So in this example, we're talking about once every 2 years, but you may have requirements that are even less than that. But if you look at the cost, the true cost, 93% of the cost of the OPEX is annualized replacement modules. So we're saying that modules typically last between 5 and 7 years in these ultra pure polish loops. So I've actually put in here the costs annually for the 7 years in order to replace the modules in year 7. But what I will say also is this, that the actual costs for the first 7 years would be expected to be just the costs of electricity and, again, the once every 2 year requirement for cleaning that we've estimated in here. So the total for an ion exchange system would be 45,600. The total, again, inclusive of the annualized cost of modules, is 10,500. So a total savings of 35,000, which is about 77%. Next slide. So that was us comparing, again, service ion exchange. Now, if we look at the other possible option, which would be single-use resin costs, right? So here, what we'd be talking about is the cost of using the resin at 60 degrees Celsius and essentially landfilling the resin after it's gone through its useful life and run out of capacity. In this example, I've estimated that that happens about 4 times per year. So if we are throwing out the resin 4 times per year, the cost that I've estimated is about $51,000 for just replacement resin. Again, there's no cost of auxiliary cooling here because you could feasibly operate this at 60 degrees Celsius continuous. So now the comparison is, again, we're using the same numbers on the electrodeionization side, so about 10,400 for EDI. And again, $51,000 if you're replacing the resin once per quarter. So total savings on this example would be about 40,500 or about 79.5% savings. And one more thing to point out, we can make changes to the comparison. In this example, I've estimated the costs of resin to be about $210 per cubic foot for anion resin and $90 per cubic foot for cation resin. Next slide. So another important piece is the assumption that I'm making is that the water coming into this process is very pure, about 1.5 microsiemen max is what I've estimated. But the more you regenerate resin, the more the advantages of CEDI and electrodeionization becomes apparent. So again, this is kind of showing you what happens if you're regenerating your resins 4 times per year versus 12 times per year. And again, the more times you're regenerating, the more you're investing in the regenerant chemicals, the labor, waste neutralization, all the things that someone regenerating those ion exchange resins would have to do. So the savings actually increase the more you would have to regenerate the resin per year. And then the green that you see here is the estimation for cooling. So 125 gallons a minute, and we've talked about this on a previous slide, we estimate to be about 31,000. So that would apply to any of these examples, whether you're regenerating it 4 times per year or 12 times per year. And then if you look at 500 gallons a minute, obviously the cooling costs increase considerably. And so also do the requirements for regenerant chemicals and resin replacement, neutralization, and the rest of that as well. So just wanted to make sure if you're using electrodeionization just on the makeup system, there is a substantial savings to be had just for the number of regenerations required for ion exchange versus EDI. And with that, next slide. I'm going to turn it over here to Clark, and he's going to run us through some frequently asked questions. Clark?
Thanks, Pat. So I think what we're going to do is just, we realize that it is a taped webinar, but we want to answer some of the frequently asked questions that usually come up when we have these discussions with customers. So the first one that generally comes up is, what are the maintenance considerations for EDI? And Mike, can you answer that?
Sure, Clark. So maintenance on an EDI is minimal and primarily consists of daily data logging. What we're looking for are trends to ensure that the pretreatment is working correctly, and so that there's no chlorine breakthrough, no hardness breakthrough, and that we're meeting the maximum feed water requirements that we specify in our documentation. We'll have you data log things like flow rates, pressure, temperature, current, volts, conductivity, resistivity, and other data. In terms of cleaning, we only recommend cleaning if the data logging indicates that you have a loss of quality of 25% or more. Otherwise, cleaning is not something that would really consider a major event here or a maintenance.
So another one that we get frequently is, how do we develop that cost model? You know, the data points, how can they use their numbers? Pat, take that.
Yeah, so it's an Excel-based comparison tool that we put together, and there definitely are a lot of details in there that we could, I guess, refine for an individual site. But we make some assumptions, some basic assumptions that I think are a good starting point for the costs of the regenerate chemicals like acid and caustic, the cost of ion exchange resin, cost of neutralization and labor. But again, those are, our initial assumptions, and we can true those up that are more site specific for you. And my suggestion would be at the end of this, we'll put up some contact information for Mike and Clark. And if you can contact them, we can work through a session where we refine those for you.
Oh, perfect. All right. So another one along those lines is the CapEx comparison. Obviously, we talked about, low capital on the resin systems. What's the CapEx comparison with EDI? Pat, you want to take that?
Yeah, a good point. And I meant to hit this a little bit earlier, but when you think about it, there really are two competing technologies against electrodeionization. There's the single use that Clark had described in the beginning. Benefit, of course, being that you can operate continuously at 60C without the added expense of the cooling. The problem is that you are creating, a waste stream out of that will need to be landfilled, and the costs that go along with that. So between that and the other competing technology, which would be service ion exchange, where someone's coming in, taking the resin and bottles out, doing the regeneration themselves, and returning them, there is a difference between those two costs that we looked at. But generally what we'd say, it's between 1 and 3 years of payback is pretty common.
Okay, perfect. Yeah. So I think the last one we'll cover is how, if they're an end user is interested in a proposal or reviewing a system, how does that work? Mike?
Sure. If you'd like a proposal, the first thing we'd like to do is understand your application and then run a projection. I would like to know some of the basics about your water quality requirements, the system flows, and the pretreatment. Once we have all that, we'd like to introduce you to one of our value-added OEM partners. These folks are extremely experienced. They've been building literally thousands of EDI systems over dozens of years, and they would take it from there and provide a final proposal. The final slide in the presentation here today has our contact information. So if you want a proposal from one of the OEMs, please feel free to reach out to us and we'll get things started.
All right, so that concludes our webinar for today. We really appreciate you participating. Please feel free to reach out to our team with any additional questions or feedback. We will be following up with emails with this contact information. So thanks everyone, and have a great day.